Welcome. Today we'll be discussing section 1.1 of the textbook. Topics today that we'll cover are types of angles, measure of angles, unit conversions, arc length and sector area, and angle arithmetic. So with trigonometry, it will be a lot about angles. How are we going to define what an angle is? Well, an angle will be made up of two rays that emanate from the same vertex, like so. So here we have just generated two different angles. One such angle is called the inner angle. I'll call that U here. This is the inner angle. And the outer angle is over here, and I'll call that V. What inner and outer are dependent on what type of system that we're looking at. Typically, it will be the smaller angle is the inner and the larger angle is the outer. And we can construct different shapes with these angles, such as a triangle. If I have a triangle that looks like this, with vertexes A, B, C, we will typically denote angle A as the inner angle for the vertex A. So angle A is here, angle B is here, angle C is here. Note that this is the inner angle because we're looking at the interior of the triangle, and the outer angle would be the outside of the triangle. Okay. We can also form arc lengths. So if I take a protractor and I make a circle here, we can say that an arc length is the distance with constant radius of a point with said angle theta. Now, this theta is also denoted as a central angle. So our arc length, as we can see here, is a portion of the circle. We can also view this as not a circle, but a disk. So if I have a disk where I'm looking at the entirety of the area, we will call a disk sector a portion of this area, for instance, here. And that is again governed by the central angle theta that is made by these two rays. So again, the disk sector is the area that is contained or made by a central angle, sometimes called a sector angle, here. Typically, we'll denote this as A ds for the area of the disk sector. Arc length here, we typically denote as L for length, and it's implied that is an arc length, but that will be in context of the problems that they're associated with. So now that we have what this is, we need to know how to make this angle have meaning. How do we measure such an angle? Well, one way that we can measure it is by the number of turns. So what is a turn? A turn is one complete rotation, or you can think of one entire circle, and it's where we contain the entirety of the arc length or the entirety of the area of a circle. So a turn is a ratio or a proportion of that. So if I have one turn, we can think of that of taking the ray and going once around the circle. Well, if I did that, I would have my first ray here and my second ray going once around the circle. I end up in the same exact spot. These angles are now coincide, meaning that they are the same. We denote this as one turn, and it is also called trivial, because we essentially didn't go anywhere. Same thing if I had a zero turn. We again would have a trivial angle because we didn't go anywhere. You can think of this one of one turn, we spun around once, where here we didn't spin around at all. This is again is a trivial angle. What if we have a half turn? Well, then we started here and we rotated around halfway. So the other ray is going this way, and we call this flat. You might also call it a line, which you'd be correct. But notice how that this has no meaningful angle as far as the inner and the outer are the exact same. Another special type of turn angle is 1/4. Here, we've gone a quarter turn, and we call this a right angle. And we typically denote it with a box to signify a corner or a right angle. Now, for the inner and outer angles still apply here. The inner angle of the right turn is what is this box denoting. The outer angle is everything else. Here, the inner angle is this half turn, and the outer angle is also a half turn. Here, the inner angle would be 0, and the outer angle will be everything else. As well as with the full turn, we have an inner angle of everything else because we went around the entire time, and an outer angle of 0. So what's interesting is, depending on the context of the situation, we can look at an angle through different lenses. For instance, if I said I have 2 turns, I could say that I spun around twice. Well, my effective stance doesn't change. I'm still looking at the same direction that I started if I just turned around twice. Turned being that I spun the entire way of seeing one side and spinning around the entire way back to the same starting point. That is 1 turn. If I do that another time, I didn't change anything, but my rotation, I can still calculate that. So now that we defined what a turn is, now we should talk about what are ways that we can make this useful as far as calculations go. One such way is radians. We define radians as 1 turn equals 2 pi radians. Now, I put them in parentheses because mathematicians say radians is the gold standard. We want to work with radians. Why? Because it makes a lot of calculations nice, as we'll see in a moment. And with this, since we always want to work with them, we're going to omit the units radians when we're talking about angles because it's implied that we're going to be using radians. So I will write them either in this parentheses notation or I will omit them entirely. I'll do that throughout the lecture to get you used to seeing radians sometimes with the parenthesis of denoting them as radians and sometimes without, but it's implied. So what about degrees? This is another standard measure of units for angles, and we denote 1 turn as 360 degrees. And here we can form a relationship between radians and degrees. And so we can say that from radians to degrees, we can write them as 2 pi radians is equal to 360 degrees because they're each equal to 1 turn, so they'd be equal to each other. But we can also divide by 2 and get pi is equal to 180 degrees. And that's the one that we really want to pay attention to. Okay. So now that we have defined ways to measure an angle, we want to be able to convert between the different measures. So if I have a quarter turn, what's that in radians? Well, we can times by the ratio that this brings up. So we have 1/4 of a turn. Write that as over 1. I'm going to times that by 2 pi radians all over 1 turn. So what I'm saying here is that there's 2 pi radians per turn. So whenever you hear the word per, think of it as like division. And when I evaluate this, I see that terms cancel. Units work much like variables. If I have an x in the numerator, x in the denominator, they can cancel. If I have terms in the numerator, terms in the denominator, they cancel as well. So that leaves us with 1/4 times 2 pi. Well, that is pi over 2. I'm going to omit radians. Okay. Well, now I want to have degrees. Well, this is equal to pi over 2 radians. I'm going to times this by the ratio of 180 degrees per pi radians. Radians cancel. Pi will cancel. And I'm left with 180 divided by 2, and I get 90 degrees. So what I found is a quarter turn is equal to pi over 2 radians, which is equal to 90 degrees. Let's see what a full turn would do. 1 turn is equal to, well, we already know that to be 2 pi radians, which is equal to 360 degrees. Okay. And we can also see that 0 would be 0 as well. Well, let's do a half now. 1/2 turn is equal to 1/2 turn times, we have 2 pi radians over 1 turn. Turn cancels. 1/2 times 2 pi. Well, that is just pi, which now we can take pi times 180 degrees over pi radians. Cancel out the pi, and we get 180 degrees. So we can say that a quarter turn or a half turn is equal to pi radians, which is equal to 180 degrees. Okay. So now we're going to introduce one more type of measure, and that is degrees, minutes, seconds. Now, how I like to think about it is that this minutes is like minutes, seconds, seconds, and think of the degrees as hours. So think of this one as hours. Why? Well, because if I was to ask you how many seconds were in an hour or how many minutes in an hour, with a little bit of thought, you could answer both those questions. We have 1 hour and we're going to times by 60 minutes per hour. Hours cancel, leaving us with 60 minutes. So there's 60 minutes is equal to 1 hour. Well, if I have 1 hour and I times by 60 minutes again over 1 hour, my hours cancel, but now I want seconds. So I times by 60 seconds per 1 minute. And now minutes cancel, giving us 60 times 60, that is 3,600 seconds. So what do we get? We get 3,600 seconds is equal to 1 hour. Now, I use this terminology because we're actually going to have degrees instead of hours. So we can think of 1 degree is equal to 60 minutes, and 1 degree is equal to 3,600 seconds. Now, you might look at this and go, okay, what's the point? This is a way to estimate the decimal part of a degree. So think about it like this. If I told you to be somewhere precisely at 12 hours point or 12.518611 hours, you look at me and go, okay, it's about an hour and a half, but no, I want you there to the second. Well, what is that? So instead, we're going to break it up into degrees, minutes, seconds, and we'll see what that is along the way. So if I said I have an angle of 12 degrees, 30 minutes, and 45 seconds, we're going to use these conversions now. So think of this as we have 12 plus 12 degrees plus 30 minutes plus 45 seconds. Okay, well, how do we go from minutes to degree? Well, we're going to have 12 degrees plus 30 minutes over 1 times, and for every degree, we have 60 minutes. Minutes will cancel, leaving us with just degrees. And now when we go to seconds, we're going to have 45 seconds over 1 times by 1 degree per 3,600 seconds. Seconds cancel, and we can add these fractions together by making a common denominator and solving it from there. Now, a generalized step is that we can jump straight to this common denominator. But let's see on what we do here. So with this common denominator, we want to have 360 be times by everything. So I could take 12. I'm going to times that by 3,600. Let me make this a little bit larger. 12 times 3,600. We're going to add 30 times 60. And then we're going to add 45 all over 3,600. And that will get us our degrees. Now, how did I get this? Well, to get the common denominator, I have 45 over 3,600. If I split this, I can see I have 45 over 3,600. Because again, we can split a fraction across subtraction and addition. Well, here, this fraction, I have 30 over 60. Well, if I times by 60 in the denominator and the numerator, I'm going to be left with 30 times 60 all over 60 times 60, which is 3,600. Lastly, I have this 12. I want to times it by 3,600 and divide it by 3,600, because then I'm essentially timesing by 1, which I'll get back 12 if I split this fraction. The 3,600 will cancel. So I can combine all this, divide, and I end up getting my answer to be 12.5186111 degrees. So now I know exactly how much time or what the angle is in the fraction component. So this is a different reference on how to estimate or effectively communicate what the decimal expansion is without having to list out a long sequence of decimals. Okay. So what are some examples of other arithmetic that we can do with this? Well, we can go the other way with this decimal minutes, seconds. Say I have 2.54 degrees. What is this in decimal minute seconds? Well, first, we're going to take the degree part here. We're going to say D is equal to 2 degrees. And we're going to just leave off the decimal. And the decimal, we're now going to take what is 0.54 degrees. We're going to times that by 1 or 60 minutes per 1 degree. Degrees cancel, which leaves us with 60 times 0.54, and that is 32.4 minutes. Well, we don't want the decimal, so we're again going to just take the 32 and say M is equal to 32 minutes. Now we're going to take the 0.4 and times it by the number of seconds. So we have minutes. Well, we know what minutes and seconds are, so we're going to have 60 seconds over 1 minute. Cancel out the minutes, leaving us with seconds. 0.4 times 60 that is 24. So we have 24 seconds, which equals RS. Thus, 2.54 degrees is equal to 2 degrees, 32 minutes, and 24 seconds. Okay? All right. So now we're going to do arithmetic with angles. And angles behave much like how you expect them to. The angles, if I was to say that I had an angle U here, and I had angle W, and that was here, defined by these two rays. Well, what would be the sum of these angles? Let's say that that's angle V. Well, angle V is equal to angle W plus angle U. They just add together. So if I had a quarter turn and I did another quarter turn, if we write that out, I start here, I have my quarter turn, and now I do another quarter turn. I have a flat angle. In other words, I have a half turn. Well, if I do one turn and then two turns, I have, or and then a second turn, I have two turns. Okay, if I have pi over 3 radians, and I want to add pi over 6 radians, it'll work the exact same way of making like denominator. So I'm going to times by 2 over 2, and I have pi over 2 plus pi all over 6. So that is 3 pi over 6. Divide by 3, I get pi over 2. Okay. This works with all the other nomenclature of decimals or degrees, minutes, seconds. But we can subtract these terms just as well. If I look at this and I say, hey, I know that this angle here, angle V, and I have this angle here, and this smaller one here, this is angle W. Well, what is angle U? Well, we have angle V minus angle W is equal to angle U. That works just as you would expect it would. So if I had 270 degrees and I wanted to subtract 140 degrees, we'll get 130 degrees. Okay. What about degrees, minutes, seconds? What if I have 130 degrees, 20 minutes, and 14 seconds? And I want to subtract 90 degrees, 12 minutes, and 7 seconds. Well, Instead of having to convert it into decimals, we can evaluate it here and see that 130 minus 90, well, that is 40 degrees. 20 minus 12, 8 minutes. 14 minus 7, 7 seconds. Some of you may be wondering, what if I had something like this? 1 degree, and let's do 20 minutes and 14 seconds again. And I'm going to subtract 0 degrees, 12 minutes, and 20 seconds. I then get a negative seconds. Well, kind of like the same thing when we subtract, we have to borrow from one of the others. So if I borrowed 1 minute, how many seconds are in a minute? 60. So by borrowing 1 minute, I have to add 60 seconds. So I'm going to have 74 seconds. I now subtract, and I have 74 minus 20, that is 54. Or sorry, 56. Sorry, 54 seconds. And then 19 minus 12, I have 5 minutes. I still have my 1 degree out front. Okay. Okay, so now we're going to cover arc length and area, sector area formulas. So with an arc length, we've been talking about these angles in terms of turns, which turns, as a reminder, is the proportion or ratio of the length versus the total length of the circle. So the total circumference. Well, unsurprisingly, we can start to see the basic concepts of this formula. For instance, we have found that the circumference is 2 pi r. R being the radius of a circle. Well, we're now going to times that by the proportion that theta of our central angle has of the entire circle. What's the entire circle? 2 pi. That's how we defined it. So now 2 pi cancels out with 2 pi, and we're left with r times theta. I'm going to rearrange that and say theta r. And what does that equal? It equals the arc length. So when we have radians, we just have to know what's our angle, what's our radius, times them together. There's our arc length. And again, we can rediscover this by saying, what's one turn? One turn is 2 pi radians. Well, 2 pi radians times r is 2 pi r, which is the circumference. Okay, so now we can look at the area. If we look at the area of a disk, we have pi r squared. But we're only going to have a portion of this. What's the proportion? our proportion is theta over 2 pi. We have this part of the disk that we want over the whole disk. Well, we can cancel out pi, and we're left with 1/2 theta times r squared. Okay? So now, when we have this 1/2 theta r squared, we can say this is equal to the area of the disk sector. So now we have an arc length formula and we have the area of a disk sector. Well, we can expand on this and say, all right, well, what if I have my radius, I have my length of an arc, and I want to know what my angle is? Well, I can rewrite this as theta equals L over R. That's my arc length divided by my radius. And that's going to get me my angle in terms of radians. Okay. Over here, we can find that what if we want to solve for theta again? We have to times by 2, divide by r squared to get theta by itself. And we get theta is equal to, and we have 2 area of the disk sector all over r squared. Okay? These two formulas have the same variables in them for the most part. What if I want to try and find a relationship between the area of the disk sector and the arc length? Well, I see a theta r squared here. I see a theta r. So that means 1/2 theta r times r is equal to my area of the disk. Well, this theta r I can rewrite as L, or my arc length. So I have 1/2 L times R equals area of my disk sector. And so here, if I want to solve for, if I had my area of a disk sector, I had my radius, I can then solve for my arc length and say that my arc length L is equal to 2 area of my disk sector divided by my radius equals L. For your check-in learning this week, the question is, solve these 3 equations in terms of R. Solve the arc length equation in terms of R, solve the area of a disk sector in terms of R, and solve the area of the disk sector in terms of arc length for R. So with this, let's have an example of real numbers. So say theta equaled pi over 4, and my radius equaled 2 centimeters. What is my arc length? Well, we look at our formula and we say, okay, theta times r equals L. And so we have 2 pi, or sorry, pi over 4 times 2 is equal to pi over 2. and I'm going to denote this as centimeters. That's my arc length. Tom, what is my disk? What is the area of the disk? Well, we have theta, or 1/2 theta times r squared equals the area of a disk. So that's 1/2 times pi over 4 times 2 squared, which this will equal 2 times 2 is 4. And we're going to divide by 4. And we're going to have another division by 2. And so we're going to have pi over 2 centimeters squared. That is the area of the disk sector. No, they're not always going to be equivalent. In fact, they're frequently not going to be equivalent. This is a random example that happened to have them be equivalent. So now that we've seen how to calculate this, let's ask another question in terms of degrees. What if I have my theta equaling, let's do 60 degrees, and my r is equal to 1, and I'm going to leave off units. Well, these formulas work with radians, so we're going to have to transition into radians. So 60 degrees is equal to 60 degrees times pi radians per 180 degrees. Degrees cancel, giving us 60 divided by 180. That is 1/3. So we get pi over 3 radians. For clarity, I'm going to denote that as radians. Okay. Now I can find my arc length. My arc length, L, is equal to theta r, which is equal to pi over 3 times 1 and equal to pi over 3. Well, this would be incorrect. You wouldn't get full points. Why? Because when I have a length of measure, so not the measure of an angle, but an actual length, it's implied that I have units here. And because I have units here, I must have units here. So I have pi over 3 units for my length. What is the area of the disk sector? Well, that's 1/2 theta r squared, which equals 1/2 pi over 3 radians times 1 squared, which equals 1/2 times pi over 3, which is pi over 6. And now I'm going to write units squared, because I had my units here for 1 being squared, so the amount of units I'd have is squared. Much like how when we had centimeters here, we had centimeters squared. So when I have an arbitrary units here, I still have an arbitrary units squared here. So with that, I'll do one more example on how to find a central angle when we're given an arc length. So say we have an area of a disk sector, and we have it being 8 centimeters squared. And we have a theta, or yeah, let's do radius. We have a radius of 2 centimeters. We want to find what our theta is equal to. And we also want to know what an arc length is equal to. Well, we can plug in to these equations. So let's first start off with this equation here. Theta is equal to 2 times the area of our disk sector all over 2 centimeters. So we get 2 to cancel. Or sorry, I should write this as R. And so we have 2 times 8 centimeters squared all over 2 centimeters squared. So there's 2 area of our disk sector over R squared. So now we have 16 centimeters squared over 4 centimeters squared. Centimeter squared cancels out, and that leaves us with 4. And again, this is implied that we're talking about a theta, so we have 4 radians. Okay. And now we want to figure out our arc length. We can say that our arc length is equal to 2 area of our disk sector over the radius, which is equal to 2 times 8 centimeters squared all over 2 centimeters. 2 cancels out with 2. 1 in the centimeters cancels out with 1 in the centimeters in the numerator. And that leaves us with 8 centimeters for our arc length. Now this shouldn't be too surprising, because if we took our radius, 2 centimeters, times our radians, 4, by this equation, we have our length being 8 centimeters. So our equations check out. As a brief summary, this was section 1.1. We did types of angles, measure of angles, unit conversions, arc length, and sector area, as well as angle arithmetic. Thank you for watching, and have a great day.